Good morning, good afternoon, good evening. We're going to give it one more minute for the rest of the folks to join us. Thank you if you're here so far. We'll be starting soon. Okay, so good morning. Hi, everyone, and welcome. I am Dan Fernandez from Edera, and I'm really excited to have you here today. So as many of you know, the AI Cyber Challenge has put a huge spotlight on the role of artificial intelligence and the role it can play in cybersecurity, since it showed us some of what's possible when we push AI to uncover and defend against vulnerabilities at scale. The big question now is, how do we apply the lessons learned from this competition for enterprise deployments? And that's exactly the point of today's session. Joining me today is Michael Brown from TrailBits, and together we're going to dive into opportunities and challenges of AI-powered security systems. And this will range from vulnerability management to agent design and a bit of deploying the systems at scale. We'll try to keep this session conversational, so we encourage you to submit your questions throughout the webinar using the Q&A feature here in Zoom. And we'll do our best to address these questions as they come up in the topics that we're covering. But also feel free to use the chat, as some of you already have, to share resources, introduce yourselves, whatever the case may be. So now, without further ado, I would like to introduce Michael Brown. Michael is the head of AI and ML security research at TrailBits. Thank you for joining us today. How are you doing?
I'm doing great. Thanks for having me, Dan.
Yeah, of course. Super excited about this conversation. So to get started, wanted to maybe begin by getting to know you a little bit better. So your background combines military aviation with AI security. So maybe could you quickly walk us through, like, how has your experience as aviation mission survivability officer and your time in the military shaped your approach to cybersecurity and threat modeling in general?
Yeah, so yeah, it's kind of an interesting story. So yeah, I went to the University of Cincinnati for my undergrad, and got my undergrad in computer science. And when I got out of the when I got out of my undergrad program, I worked for about a year doing full stack web development, and kind of found it honestly to be a little I guess not interesting, or I mean, the work was challenging, but I just wasn't like super passionate about it. And I had been considering military service for a long time. I was actually in ROTC in college, um, but didn't actually commission through that program. So, after about a year, I kind of just went and did something completely different. And I joined the military, and I ended up flying helicopters because that was the hardest thing I could think of to do at the time. So yeah, I did that for about 8 years, but kind of ended up back in computing, back in cybersecurity. As I got to the end of my 8 years in the military, I was kind of having like life changes. I got married, was about to have kids. So I decided that, I didn't want to be gone all the time and absent from my family. Even when I was stateside, I was still gone 6 months out of the year, training exercises in the field, that kind of thing. So in my last 2 years in the military, I went and got my master's degree from Georgia Tech in CS. And while I was there, I got exposed to a lot of really interesting software analysis research, a lot of really interesting cybersecurity research, and kind of decided that's what I wanted to do. So after I got out of the military, I I started working in a research lab at Georgia Tech. Was also in parallel doing a PhD, which I did not finish. I got to like the all but dissertation point, so I'd done all the research, but by that point, I'd kind of worked myself out of the need to go through the back end part of the PhD. And so, ever since then, around that time, I also joined Trail of Bits, and we've been working on some really interesting and really kind of crazy software security intersection with compilers, AIML type security problems for the last 3 or 4 years here at Trail of Bits, and really the last like 8 to 10 years, just for me as a researcher in general.
That's awesome. Yeah, it's always great to hear about origin stories, and maybe now let's like the deep dive into the nuances of the challenge. So while there's a lot of debate about
Hmm.
and discussions of using AI for vulnerability management, the challenge outlined very specific tasks, many of which require specialized workflows. So you first had to
Hmm.
find vulnerabilities and prove that they existed with a POC, then generate patches that correctly address the vulnerability that was found,
Hmm.
then maintain the functionality of whatever open source project it was that you were addressing or application. And then there was a strict verification for accuracy to kind of like
Right.
penalize the submissions that were not, to avoid kind of like sending low quality submissions by the team. So and the competition seemed to highlight like distinct philosophies and approaches to solving the problem. So maybe can you walk us through like what were the different approaches with like pure AI approach versus hybrid? Which one did you
Hmm.
choose and why?
Yeah, yeah, for sure. So yeah, DARPA did a great job of kind of creating this challenge. And one of the things that's kind of lost when you talk about all the individual rules is kind of what motivated them. And really, what they wanted was for the technologies that were created by the competitors in this program to actually be usable in a way that would really change the game for securing open source software. So part of the reason why all these rules existed, why we had to have crashing test cases for proving the existence of a vulnerability, why we had to have high quality patches that both fixed the vulnerability and also did not break other existing functionality, is because DARPA eventually wants, cyber reasoning systems like the one that my team and I built, Buttercup. They want these to be able to actually be used to secure open source software at scale. So they try to make it as realistic as possible with as few adjustments as necessary to make it into a competition as possible. And I think they did a really great job. So um, because of this, we have the constraints on the project are mostly in terms of the artifacts you had to produce. So when it came to finding a vulnerability, it wasn't enough just to say, "Hey, I think there's a vulnerability on line 50 of main.c." And this is because we have tools that do this already, static security scanning tools, um, plenty of large language model driven tools that do the same purpose. But the problem is they're subject to false positives and true positives. So if we have a tool that goes out and just reports a bunch of vulnerabilities to open source maintainers, they're just going to ignore them because they don't have the time. They barely have the time to maintain these software packages in the first place, much less the time to go filter out someone else's false positives. So we had to have some sort of proof of vulnerability, which is a test case, an actual input you can feed the vulnerable program that will reliably reproduce either a sanitizer being triggered, or a crash in the program, or an infinite loop. And for all the computer science majors out there, we detected infinite loops with a timeout. We didn't actually solve the halting problem or anything like that. So so no Nobel Prizes being given out for these things. But and then when it came to patching, when you produced a patch, it had to, one, it had to compile, and two, it had to fix the vulnerability. Meaning when I run this POV or this proof of vulnerability, that we actually don't see the vulnerability trigger anymore. That's how we know we fixed it. So that's another part of the reason why DARPA made the choice to require, at least for the semifinals, they kind of relaxed this a bit, but you still more or less had to come up with proofs of vulnerability for patches. So these constraints didn't really constrain us in how we went about our approach to the problem, but they definitely constrained you in terms of your approach had to fulfill these requirements. Um, so we, from the beginning, we have been working with AIML technologies and security technologies and where they intersect, and doing novel research in this area since before the large language model became kind of the predominant form of AIML technology. I worked on a number of DARPA programs as early as in 2019 that were working on vulnerability detection using graph-based ML methods, a variety of other methods. back then natural language processing was being used, but it was not quite as good as some of these other methods. So I was in kind of a unique position where I was, at the risk of sounding like a hipster, I was doing AI for security before it was cool. So going into this competition, we kind of knew very plainly what the limitations of large language models were in this space, because we had been working on other approaches in this space. So from the beginning, with the original concept that I built along with my co-creator, Ian Smith, he was the other person who helped me write the original concept that DARPA picked up for this competition. We always went at this with a hybrid approach of we recognize the fact that large language models, AI/ML, whatever term you want to use, they're really good at certain types of problems. Conventional software analysis, like fuzzing, like static analysis, they're really good for other certain types of problems. But we typically find that these types of problems are complementary, meaning that the problems there's little overlap between the problems that AI solves better versus the ones that conventional solves better. So we broke down the problem. We looked at end to end. What did we have to do to win in this competition? And for each substage, for each piece of this competition, we said, what's the best approach that we can use? And we picked, well, this is going to be an AI/ML approach, or this is going to be a conventional approach. And we stitched those together into a pipeline. And ultimately, we came up with a winning solution. So our hybrid approach uses AI/ML for some things, uses mostly conventional approaches for other things. And we were able to take second place with this approach. The first place finisher was Team Atlanta. They're from Georgia Tech. So my alma mater, I wasn't involved in their team at all, but they took first place, and they had a similar approach where they were very much a combination of the two best of both worlds technologies. The third place finisher was Team Theory. They're a security organization that's mostly in South Korea, but also has a presence in Austin, Texas. They had a little bit more of an LLM forward approach, where they had a much higher tolerance for false positives or basically less accuracy than our approaches did, and they were able to take third place with it. But if you take a look at the accuracy or relative accuracy of the systems, when DARPA kind of reported the final scores, we were one of the most accurate teams out there. We had about 90% accuracy, meaning some of the patches that we submitted, we later actually went back and fixed, because we found out that they weren't fully generalized. They would fix some POVs, but not all POVs. So we went back and fixed some of those. We got dinged on accuracy for that. But Team Theory, they were about 45% accurate, which meant, for about every one patch they submitted one that ended up being a false positive. Either it didn't work, or it tried to patch a vulnerability that didn't exist. And as a result, their score was kind of penalized for that. So in some ways, it might have been why they were in third place, because they were a little bit more speculative. They might have been able to beat out some other teams, but it's also possible that by being less accurate, that might have been what dropped them out of second place or first place. So we don't really know, because we haven't really Trail of Bits. We don't have access to their data, like the kind of stuff that like the vulnerabilities they found and exactly how they found them or how they patched them. But I think it's an interesting question between a hybrid approach versus a fully AI/ML approach. Like how much did it help them beat the other 4 teams that they beat, and how much did it prevent them from beating the 2 teams that came in front of them? It's kind of an interesting question that we don't know the answer to quite yet.
Excellent. Yeah, that's super interesting for sure. So I think that's a good segue to both transition to another topic and maybe start addressing some of the questions that have come up. So in terms of the technicalities of the implementation, so I'm sure there are other fellow ML nerds in the audience that want to dig deeper into about the architecture and the technical details. And could you elaborate maybe a little bit to start with one of the questions from the audience that is related to how did your team implement deduplication of vulnerabilities? So assuming you're processing a dozen or multiple repositories at once and you start to get initial findings, what does the workflow of the application that you develop look like to kind of like start to acknowledge the things you have seen before and potentially duplicate vulnerabilities?
Yeah, so Buttercup uses a fuzzer, OSS fuzz, and cluster fuzz primarily to find vulnerabilities. We have this augmented with a large language model based accelerator that helps it saturate coverage on fuzzing harnesses faster. It also tries to generate inputs that are more likely to trigger vulnerabilities versus just kind of more commodity bugs more quickly. But for the most part, it is fuzzing. So as when the fuzzer finds a crash, we get a stack trace. We get a stack trace of exactly how deep, where the line was triggered, or what line triggered the vulnerability or triggered the sanitizer. And this is the basis for how we deduplicate vulnerabilities. So what we mean by that is we'll take a look at the stack traces for two given vulnerabilities, and if they're identical or very, very close within a kind of a small fuzzy threshold, they functionally had to be basically equivalent, the exact same stack trace. We would consider those two vulnerabilities duplicates of each other, and we would treat them as such as we process future vulnerabilities. Now, that being said, sometimes the same root cause vulnerability might be reachable from two very distinct call graphs. So we couldn't always rely on this. So we actually had a higher level of deduplication that would take a look at the POVs that we had generated, the proofs of vulnerability, versus the actual patches. So for example, if we found a new proof of vulnerability, we find a new crashing test case, we would actually run it against the patches that we had already created. And if any of these patches fix the bug, well, then the bug is a duplicate of something else that we've already seen. So we had no reason to submit it again. And likewise, if a likewise, if a vulnerability broke a patch that existed before, meaning it's still triggered, we either know now that this is either a distinct vulnerability on its own, or perhaps it is a case where the patch wasn't fully generalized. So the vulnerabilities that had the same stack traces, even though we consider them duplicates, we actually reran those duplicates that we found in that lower level of deduplication against patches that were made for, I guess, the original or the baseline vulnerability, to make sure that our patches were actually high quality. Because sometimes you can't eliminate the possibility that a large language model, when you ask it to generate a patch, you can't eliminate the possibility that even through very careful prompting, that it'll just try to make a patch that checks, if the input equals the POV exit. And those are kind of the patches that the conference organizers or the competition organizers would specifically go back and look for and mark as ineligible patches or mark them as incorrect. So we had to make sure that we were forcing the large language model to actually do its job, and that was one of the ways we did it.
Excellent. Yeah. So maybe let's double click on that patching approach and strategy. So maybe if you could elaborate, like there might be some more complex workflows, especially when you're creating a larger patch, and your team, if I recall correctly, generated one of the longer in terms of like lines of code that the patch was to address the different vulnerabilities. Like what would make it possible to make such a complex solution? I guess how did you go about generating that? And to tie it to one of the questions in the audience, I guess how did you ultimately test the code that is, if it was generated by a LLM, how did you go about that?
Yeah, this is a great question. The patching component within Buttercup was probably the most complex piece of technology we actually built. So it's actually really vindicating too, because when we first started working on the AI Cyber Challenge, this was like 2 years ago, which is like 5 lifetimes in terms of like the acceleration of AI and how people are using it day to day. And so back then, the whole idea of like agentic systems or multi-agentic systems didn't really exist. We had seen a paper on Archive about a month before we started building it that had talked about solving complex problems being more amenable for multi-agent systems. So we actually pioneered one of the, through Buttercup, one of the most complex and successful multi-agent AI systems, because we created a patching system that uses 4 or 5, depending on how you count them, distinct agents that all have a different persona, a different prompt, and a different goal. And we created a workflow between them for them to pass this around. So ultimately, that's what allowed us to create large patches. It was because we weren't incentivizing the large language model through this really long and complicated prompt to just take the easiest and quickest response. We actually forced it through its multi-agent structure to validate itself along the way. So the way this works is we equipped some of the patching agents with tools in the form of the ability to build, a patched version of the software with the ability to run unit tests and other functional tests that we were provided by the competition organizers, and the ability to run the original proof of vulnerability. So the leader agent for this entire patching system will task a agent that we call the software engineer agent to fix a bug. So we'd say, hey, you have a bug in your system. I found this crash and it has this security vulnerability associated with it. I need you to fix it. So this agent is prompted to go, work as a software engineer doing normal maintenance on their program. When they produce a patch, we then have a QA agent who says, hey, you're in charge of making sure this thing actually works. Here's the tools that you have available to you to use this. So this agent will actually go, make sure that, and to be determined, or to be, fully clear, some of this is deterministic logic within this agent. It will actually go try to build the software with the patch. And if it fails, it will send it back to the software engineer and say, hey, this thing doesn't even compile. Why'd you give me this? And then that cycle will continue until it produces something that does compile. And then we say, hey, this does or does not actually fix the vulnerability. When I run the vulnerability, it still triggers, or it doesn't trigger. Good job. And then finally, the third step for validation is, hey, we're running these unit tests and they are/are not working. Good job. So the QA agent takes care of this piece. Eventually, the QA agent will get kind of stuck, and sometimes the software engineering agent gets stuck. And for them, we have almost like a therapist, a reflection agent. This reflection agent will be given a kind of like a security engineer persona. And it says, hey, you're a security engineer. You're trying to help the software engineer fix this bug, but he's having trouble. And the QA agent is also having trouble fixing it. So this will then have, more of a security engineer mindset, and provide them information that they need to get unstuck. So ultimately, this workflow is allowed to continue subject to a timeout. And ultimately, it can eventually produce very large patches for really complicated bugs, because it has the ability to reflect and iterate on patches that almost work. So for example, if the software engineering agent produces something that compiles and fixes the POV, but it breaks other functionality, and let's say this patch is only maybe 100 lines long, the reflection agent enables it to go through and, instead of just throwing the whole thing away and starting over, maybe add the extra 100 lines necessary to patch other functionality that depends upon the code snippet that we had to fix the vulnerability within. If, for example, it changes like an API, or something else. So ultimately, it's because we have a really complicated patcher, multiple agents with different goals working together to ultimately produce a viable patch. That's how we end up with complex outputs. It's a function of the complex system we built.
Excellent. Yeah, and you also avoid compounding errors by just having like a one-shot approach, where instead you're like continuously iterating through the whole process. So the other thing that comes to mind is that obviously there's a wide variety of models that are available out there. It seems like almost every week or every month there's a new iteration, maybe a distilled version of a model that is more effective at doing certain tasks and things of that nature. And I think you also maybe you obviously had choices on the LLM component that you chose for your ultimate solution. And one thing that comes to mind there is like the ongoing debate about like, do you need a super generalized, extremely large language model, or do you go for the non-reasoning approach or non-reasoning model to solve the problem? So maybe can you walk us through like, how do you go about choosing the model for, and maybe based on your description of the different tasks that are happening along the way, it sounds like it's possible to use multiple different models for different functions. So how did you go about that?
Yeah. So when we first started in the AI Cyber Challenge, like I said, it was 2 years and five five lifetimes ago in terms of how what was available and how sophisticated the AI technologies were. So back when we started, we had access to I think it was like GPT 3.5. It's corollary from Anthropic and like Gemini 1.5. Reasoning models hadn't come out. In fact, reasoning models came out after the semifinal competition for the AI Cyber Challenge completed. The reasoning models were available for the second round. But what we had found is that in order to do all the problem breakdown, decomposition, task or technique selection that we had done, we had actually, basically embedded our subject matter expertise as cyber engineers or security engineers into the design of this system. So if you look at the kinds of things that reasoning models are doing in order to solve more generic, less specified problems, they're doing a lot of problem breakdown, a lot of step-by-step analysis, and we'd actually already kind of baked this into the system. So when we were testing our second version of Buttercup that went to the finals, we had the ability to use reasoning models, but we found that all they did was ended up just costing us more because we had already constrained how we were using large language models to very high context, very narrow, very specific problem sets where we were very likely to get a good result, and also where it was very easy for us to verify the result before continuing to eliminate the compounding error effect that you mentioned before. So when it came down to it, we actually ended up in the finals not using any reasoning models at all. So in this case, the more sophisticated, more expensive models didn't really help us because, best case scenario, all they were going to do is reproduce the problem breakdown steps that we had already kind of concretely outlined for the system in more deterministic ways. So that really helped us keep the error rate down, and part of the reason why we were able to be so accurate throughout how we built the system. As far as like what specific models we used, we found that anthropic models were better at helping us generate seed inputs to improve fuzzing. So we use Anthropic for that AI component, and we found that the GPT line of models, I think we were using GPT-4, yeah, it was GPT-4 and Sonnet for the Anthropic piece, but we found that GPT-4 was better at writing patches. So we actually used both of those models. The performance downgrade wasn't significant going down to the other models, so we actually used those as backups. So that way, if we had an upstream failure for one of the model providers during the competition, we would fail over to the other provider. And so I do want to say that just because we chose Anthropic for one piece and OpenAI for another, doesn't mean that there was like a serious downgrade in performance. It was small enough that like there was a wide enough margin that it made sense to choose a particular model over the other, but not so much that it meant that we couldn't use the other as a backup.
Yeah, that's super interesting, and I'll definitely go back to the cost perspective, and I think that was one of the bigger constraints once we get to like how to deploy these at scale. But based on one of the questions from the audience around security, maybe let's quickly cover, or maybe not so quickly cover, the threat modeling for these systems. So in terms of like creating a tool like the one that you just created, assuming it's running in a production environment, it starts to get access to potentially your entire code base. You may want to run it across like, I guess, a lot of repositories in general. It's like, what would you say are the most critical threat vectors against systems like the ones you developed? And yeah, let's maybe start there.
Yeah, so one of the good things about Buttercup and really all the cyber reasoning systems that competed in the AI Cyber Challenge is they don't allow free-form input from an end user. So we actually have I think, kind of more tractable threat model for deploying this at production at scale than other types of AI ML systems. So I want to caveat that right off the bat that we have an easier version of the problem than your average like product manager or product security manager that's making a more open tool. So Buttercup, it requires access to an open source code repository. That code repository has to have like a reliable build script because we need to be able to build it with sanitizers. We need to be able to build it with a new patch. And it also needs to have access to the source code so we can scan it. And it also needs to have a reliable way for us to fuzz it with input. So it needs to have, at the very least, a rudimentary fuzzing harness. And that is actually not as challenging of or that's actually not as high a bar as I think most people think. We were actually piggybacking off of OSS Fuzz, which is Google's at-scale fuzzing solution. So many of the open source software repositories that we targeted within the AI Cyber Challenge, they actually already had ready-made fuzzing harnesses, and a lot of people have opted into this program by writing fuzzing harnesses for the software that they maintain. So that's probably like the biggest hurdle that we have in terms of like what regular open source software, what regular software looks like versus the targets in AI Cyber Challenges that they did have fuzzing harnesses, but I want to stress that it's not really that big of a hurdle to create these. So ultimately, we don't really have to worry about things like prompt injection because our prompts are closed. They are within the system, and they are more or less static. Um, so we aren't actually putting into the context window anything other than, for the purposes of patching and for seed generation, some of the source code itself. So we do have to worry about, to a certain degree, the likelihood that a malicious commit or a like a malicious piece of documentation gets edited by a contributor to the open source program, and they try to inject commands, or try to inject things to otherwise change the behavior of our systems. Um, so yeah, that's like a real thing, but it's much harder to pull off, because oftentimes the amount of text you need to perform a realistic prompt injection in the presence of guardrails is fairly significant. So it's going to be really hard to disguise a commit to, like, let's say, a README file that has all of this stuff in there without an actual project maintainer seeing it. So in some ways, like I said, we have kind of an easy version of the problem. If people are inserting, let's say, for example, code comments into the program, we actually strip the code comments out. We only look at the actual source code itself. So we do have some kind of input sanitation that we deal when we're actually analyzing raw code. But for the most part, this kind of adversarial stuff was out of scope for the competition. So right now, as it stands, like, Buttercup has no active guardrails for defending against this kinds of thing. It is on our development roadmap for ultimately, like, putting that in, so that we have a stronger security posture with respect to like prompt injections that come in through the software itself that we're analyzing, or through its documentation. But realistically, that's a much more constrained threat model than I think the average user facing AI enabled application is going to have.
Got it. Yeah, no, that's super interesting. Now, in terms of when deploying, thinking about and maybe covering a little bit of the roadmap of what you're considering on doing, like, are there specific trust boundaries that, given the architecture of your application, you may want to have, where maybe you want to have like isolated boundaries for like testing AI generated code, or maybe severing access from one type of agent to a different type of agent in case the adjacent infrastructure was compromised, or anything of that sort?
Yeah, so I think this is where we get some extra benefits from the design architecture that we chose for Buttercup, and then I think this is something that you would largely also be able to realize for non-Buttercup type AI enabled systems. So the idea here is this idea of trying to fix these compounding errors by having small, constrained, context-rich problems for large language models, instead of one giant problem that it can iterate on and autonomously pull in its own input sources that you now have to worry about being a source of poisoning for data, or a source of prompt injection, et cetera. Depending on whatever kind of model you're using, you have to worry about, for long-ended or long-tailed complicated problems. You have to worry about, particularly when you give the large language model access to really open-ended tools, like you let it search the internet. Now you really have to worry about prompt injection, because you're not actually sure deterministically what it's going to pull down, what it's going to feed into. So by using some of these smaller, more deterministic applications of large language models, even though the large language model itself is non-deterministic and vulnerable, and inserting these validation steps in between each of these applications, it's a natural place for you to install security controls. And it's also a natural place where trust boundaries arise. So for example, when we are trying to, in the first stage of Buttercup, trying to generate proofs of vulnerability, we give a large language model access to the only specifically code snippets that we control, that have commentary stripped out, and documentation if we deem it to be relevant, but we really don't use a whole lot of that, and it's pretty specific if we do use it. But either way, the purpose of this phase of the system is to produce crashing inputs. So even if you manage to convince my AI agent to do something different because you've injected something into the code, that malicious output will not propagate unless it is in the form of a crashing test case that I can run against the program. So what it does is it really constrains the amount of entropy, or the amount of space an attacker might have to move on to the next step. this is less likely to, or you're less likely to be able to use this to your advantage if you have a long-ended, very complicated problem and you're relying on the model to fill in all of your problem breakdown gaps. For example, like a reasoning model. So I'm a big proponent of building AI ML systems that make deterministic what can be made deterministic, and to use really context-rich, constrained applications of AI where you have a very tight validation control for the outputs they produce, and they are decoupled from the operations of other AI agents. So even within our patching system, the multi-agent system, even within that one application of AI, we have the ability to validate in between, passing information back and forth between these agents. And that ultimately helps us create and will help others create AI-enabled systems that have a pretty decent security posture, as compared to very open-ended and very like kind of wild west applications of AI.
Got it. Yeah, and now thinking about enterprise deployment, one of the questions that has been added to the Q&A here is like, how would you determine? So there's going to be a two-part question. I'll start with the question for the audience, and then I'll add a second part. How would you determine how long to run Buttercup on a given target? Is it time bound? How do you assign that time bound? And does it need to be more complex for? Does it need to be longer for more complex software? And then I guess follow up with like, how do you deploy this at scale in general? It's like if you have to do it for 1,000 runs versus 100,000 runs in a production environment, what does that look like?
Yeah, these are great questions. So to answer the first part, a lot of this depends on the quality of the fuzzing harness. So we measure the effectiveness of fuzzing on a given fuzzing harness by its code coverage. So if you have a fuzzing harness that directs inputs that the fuzzer is creating to a very narrow, a very small slice of functionality within the program, the coverage is going to reach 100% very quickly. And once we get to 100%, we'll still sample and we'll still fuzz along that branch. But ultimately, it becomes a lower priority than fuzzing harnesses that have poor coverage. So if you have a fuzzing harness that basically just is a very narrow shim that just kind of throws bytes into the program, in that case, you typically see very low coverage because the fuzzer will generate a lot of inputs that don't make it past the input parsing logic. And they don't have a lot of like formatting that helps the fuzzer reach deeper areas. So that's an area where our large language model will help it try to craft inputs that are likely to pass through there to serve as seeds, so that the fuzzing harness can then achieve a higher degree of coverage. So within Buttercup, we would prioritize fuzzing harnesses that had poor code coverage, and we would also prioritize them for AI assistance. But ultimately, when it comes to how long we ran fuzzing campaigns, we ran them until the competition told us we were no longer eligible to score points on that challenge problem. All the challenge problems had an expiration date. So we kind of had an artificial constraint or an artificial endpoint within the AI cyber challenge, but in reality, if I was deploying it at scale and I had to decide when I want to stop doing this, I would probably use some combination of saturation of those fuzzing harnesses. How well did my model like actually cover the code within those fuzzing harnesses, as well as some metrics that we would derive from the AI-enabled seed generation component in terms of how often did I run tasks that were tuned primarily for vulnerability discovery versus code coverage expansion. We actually had two kind of subnodes within the seed generation or the AI-enabled seed generation component to do kind of two subtly different things. Our endpoint would be we've reached saturation on the fuzzing harnesses, and we've also reached saturation on the types of modes our AI can do, our AI assistant can help out with. So getting to the second part of this is, like how would we deploy this and how would we run something like this at scale? This is something that we mulled over quite a bit at Trail of Bits. And actually, after we finished submitting our final version of Buttercup, which was in mid to late June, we actually didn't take our foot off the gas. We had about a month and a half until DEF CON, where they were going to release the results. We spent that month and a half creating a standalone version of Buttercup and making it open source that you can go, and it basically means anyone can use Buttercup. The original version of Buttercup that we created for the finals competition, it had to run at scale. It had like $100,000 plus in budget between compute on an Azure instance for all of our compute requirements and like a ridiculously high LLM budget. Of which we used only about $40,000 over the course of several days. And a lot of that was because we were trying to use the money that they gave us to leave no stone unturned. But realistically, it could consume a lot less. So that was the original scale. And it was also really like kind of coupled to the competition infrastructure. We had API hooks for submitting things to the infrastructure, getting word back whether or not they were accepted, given points or whatever, so we would know what to do next. So we made this version of Buttercup that is now available at Trailbits on our GitHub organization. That's fully open source, but also you can run it on your laptop. So you don't need $40,000 in 6 days and a bunch of Azure nodes to run this thing anymore. You can run a small version of it on your laptop. You can use it for vulnerability research if you're an independent security researcher. If you're an organization, you can deploy it still using a lot of the same deployment infrastructure that we had for the AI Cyber Challenge. You can deploy it at a smaller scale that fits your organization. And if you're a big organization, you can go deploy the $100,000 version of it and and go turn a lot of money into server heat. So that's one of the great things about Buttercup. In terms of like how you would scale it for your specific organization, it depends on the kind of software you're trying to analyze, how complicated it is, how many different projects, what your budget is, how long you want to run it, and all those things could factor into it. And if you really do find yourself in a position where you have those questions, please reach out to us. We'd be thrilled to hear that people are using Buttercup at that kind of level, and we'd be happy to kind of give you some advice along the way.
Awesome. Yeah. And now when thinking about, so you mentioned some of the metrics or some of the budgets that the team had to work with. I suspect there was a lot of thought and effort that went into adding visibility maybe to the different stages of the pipeline when you were trying to optimize for certain things. So now thinking about like how you went about making incremental improvements to the final product and your solution, like what kind of visibility and controls did you also have, like human in the loop type workflows that were powered by that visibility?
Yeah, so another really great question. There's a couple of things that we've made changes to from our competition version to make them a little bit more amenable to having a human in the loop. But ultimately, you can still run Buttercup in its fully autonomous mode. So one thing that we've done with Buttercup is we've made it, we've equipped it with telemetry. So it's got it broadcasts its functions, it broadcasts its LLM queries, it broadcasts basically everything it's doing, including system logs, to a Signals endpoint. So and we've actually made it so that Buttercup will deploy its own. So you don't even have to go through the trouble of setting one up within your organization and doing all this. It has its own local Signals endpoint that it will deploy this information to, that you can log into with a web interface. And you can actually watch all the things that it's doing. And you can set up a dashboard to see, okay, these are the vulnerabilities it found and all this other great stuff. Not everybody wants to use telemetry. So we also have a web interface. What we did was we kind of took out the competition API and we replaced it with our own user interface. And that was to kind of keep the changes that we had to make to Buttercup minimal. So now instead of the competition telling us whether or not we're doing the right things or telling us that our vulnerabilities that we found are correct or not, we actually have a user interface where a web-based user interface where the person using Buttercup can pull up a web browser and interact with the cyber reasoning system. And you can see the vulnerabilities it's finding. You can see the patches it's making to try and correct those vulnerabilities. And more importantly, you can actually now tell the system that you consider a patch to be incorrect. So let's say you do have a situation where you find a vulnerability, the system generates a patch, but the patch is something naively dumb that just says, oh, hey, if I see this POV, if I see this specially crafted input, just exit out of the program. Technically, that solves the problem. Technically, it doesn't break any functionality, but it's not really actually fixing the program. We want the program to be like resilient in the face of failures. So now the user can actually mark that patch as being incorrect, the same way the competition organizers would have. And that user interface then sends it back to Buttercup and says, no, you need to retry patching. So now what we've done is we've kind of created this user interface that lets the user use Buttercup, but now the final output is actually a patch that the user can validate and the user can understand and read. And then ultimately, this brings us like 95% of the way to opening a pull request. The only thing that's kind of missing there is what we typically see in a pull request, which is the free form description of like the free text version of like, okay, here's the vulnerability you found, here's how you trigger it, here's steps to reproduce, and then also the description of what the patch does. But that's just one LLM query away from generating that the user can do on their own, and that we might eventually make part of Buttercup. So we're very, very close to the point now where an individual user running Buttercup can go end to end. All they have to do as the human on top of the loop is actually validate that what they're seeing is something that they want to submit as a pull request to a maintainer and that they hopefully merge.
Yeah, that's super helpful. Like having the ability to automate some of those, I guess, more manual tasks that don't allow you to integrate code sometimes definitely goes a long way. So for this last section, I wanted to touch on a little bit. So a lot of this conversation highlights all the great uses for this technology, but when we talk about this in general, there's always going to be the debate about like the dual use kind of like dilemma with not necessarily with your tool, but just with large language models in general. So the same techniques that your team use for powering a solution for defensive purposes could be used for potentially compressing the time window to generate a POC for a malicious actor, kind of speak. So what's your take on that in general? And like, how does this change the strategic landscape for both defenders and like white hat kind of security research?
Yeah, so I actually kind of I know this is not your idea, so this is not directed at you. I kind of reject this idea in general, and here's why. When it comes to what Buttercup does, if you fundamentally look at the problem of I have a vulnerability and I can do two things with it, I can patch it or I can exploit it. And typically, when we're talking about exploitation, we're talking about something a little bit more complicated than like a simple denial of service or a simple just like just you let it crash. So when we're talking about exploitation, admittedly, I'm pushing the bar up to something where you actually are able to extract data. You're able to achieve some sort of like foothold on a system through this vulnerability. Um, so I just want to clarify that when I make this next statement. The next statement is that patching a vulnerability is a problem that is one or two orders of magnitude less complex than exploiting a vulnerability. So, and also when it comes to exploiting systems in really complex and dangerous and scary ways, the bottleneck for that has never been vulnerability discovery. There's always been a bountiful number of vulnerabilities at varying degrees of exploitability. What has been the bottleneck for the kinds of like, really like nightmare scenario types of exploits has always been, can I find a vulnerability? Can I find a vulnerability that's exploitable enough to let me do something, really, really kind of crazy with it? And can I make the vulnerability reliable? Can I get it to land at a reliable rate? Because in many cases, a lot of these vulnerabilities are kind of non-deterministic. We start talking about like kind of like heap exploits. So ultimately, in terms of the technology that we built for Buttercup, yeah, it's going to help people find vulnerabilities. But attackers already had plenty of end days to choose from before we went about this. There's plenty of unpatched systems out there, plenty of unpatched software libraries from the open source ecosystem. So we're not really helping attackers by creating more vulnerabilities. They've already got a big basket of vulnerabilities to choose from. And there's no easy way to take the patching system that we've built and then say, go exploit. I mean, you could do a control replace across all of the prompts and say, everywhere it says generate a patch, say generate an exploit for the system. But the quality of the output that you're going to get when you change to exploitation is not going to be the level of quality that we get for patching. And there's two reasons for that. The first reason is that patching is something that current models are very well suited for. One of the most obvious value propositions for large language models today is generating code. So a lot of the models have been tuned to do a very good job at generating code, particularly for open source code bases, because they've all been ingested and put into the data set. So one, the models are very, very good at generating code, but generating exploits is not something that we have. We don't have like a GitHub scale code repository for exploits, but we do have GitHub like massive internet scale data sets for generated code. And the second is that when we talk about patching software, it allows the large language model to kind of have this like kind of flat view of a system. And by that, I mean, it can look at static code, and it can write static code, it can patch static code, and then, we hope that at runtime, it's going to fix it. You don't get to take that kind of shortcut when it comes to exploitation. When it comes to exploitation, what really matters is what happens at runtime. And it's really hard to build tools that will arbitrarily let an agentic AI system try to go exploit something, understand what is coming back, and then go out and kind of re-exploit it, or reiterate on that exploit until it lands. So ultimately, my position on this is that these kinds of technologies that were developed for the AI cyber challenge are a boon for defenders, because now we have the ability to kind of tip the scales and apply vulnerability detection and remediation at scale for a commodity amount of money. I think we're talking like somewhere in the order of, most conservatively, a couple $1,000s per vulnerability, and most optimistically, we're talking like $150 per vulnerability. So for either way, it's for a commodity amount of money compared to hiring a security engineer. We can go find bugs that are admittedly a little bit more low hanging fruit or medium hanging fruit. We'll still have security experts to go find the very nasty, kind of sticky, weird, logic based bugs out there. But we've done all this for cyber defenders. There's no readily accessible way for a cyber attacker to take what we built and then just give them the keys to the kingdom to exploiting something. You would need an entirely different system. That system would need access to models that are 1 to 2 orders of magnitude more capable than the models that we have today, and a system that is 1 to 2 orders of magnitude more complex than the one that we built in Buttercup in order to be able to do that. That's my take based on what I've seen in the industry.
Yeah, and I think that's generally good news and good to hear. And I know we're coming close to the end here, so I guess the next few questions we can do them in like rapid fire kind of approach, so we cover like the rest of the ones that are open from the audience here. So the first one is like for the competition, is there anything else that you were hoping to prove or demonstrate that you were unable to because of a constraint?
Yeah, so originally, the original concept that I wrote up for Buttercup had to be cut down quite a bit because we wrote the concept before DARPA had published their rules about what you would actually be able to do. So there's actually a lot of stuff that we wanted to do that we had to cut out. Some of it included using static analysis to find vulnerabilities that we, without necessarily finding a proof of vulnerability, without necessarily finding a crashing test case, and then trying to patch those vulnerabilities. That ended up being something that you were able to do in the finals. They had relaxed the constraint that you had to have a POV, but they did not change the scoring algorithm. The scoring algorithm still heavily incentivized you to find POVs. So we actually ended up sticking with our strategy of not trying to patch anything unless we had a POV, because one, it meant we could validate. The presence of the POV allows you to validate a patch, and vice versa. The presence of a POV lets you know that the patch actually is fixing a real bug. And then there was also a couple of other things that we wanted to do that were actually kind of considered, I won't say like illegal, but they were kind of like, memorizing the tests. So there was a couple of things in there that were a little, I guess you would say, kind of controversial in terms of whether or not they actually would help or whether they were just kind of gaming the competition. But I was fortunate. I was actually kind of happy to see that they wouldn't be allowed, because that meant we had to rely a little bit more on our merits. But yeah, I would have liked to see a little bit more room for static code analysis to live. And in fact, it's one of the things I really admire about the Team Theory's third place finishing CRS, is that they put a lot of focus on trying to use static analysis and reduce the false positive rate that you get from those tools with large language models to get down to vulnerability alerts that they consider to be highly likely to be real, and then go patch those as if they were real.
Got it. Yeah, and one thing that you brought up in the answer to the previous question was kind of like making a clear distinction between what this technology is good for and what humans are good for. So in the context of, I guess, penetration testing and in general, there's some discussions about like, hey, can you automate X percentage of the task, or like for writing software in general? Like, how do you summarize like how these tools are, what they're great at versus what humans continue to be like significantly better in?
Yeah, so I kind of look at this in two ways, and I've kind of come across this way to describe this to people, mainly for folks. So, like in the early days of AI and cybersecurity, when they intermixed, we had a lot of like security experts who didn't know how to do anything with AI, and they would make stuff that like was kind of like wonky and kind of broken. Then you had AI experts or ML folks who would try to jump into like applying it to a security domain, and it would kind of like not work out great. And part of it was that there was no overlap of skills that allowed people to do good problem formulation. And what I mean by that is problems tend to lend themselves better to two different types of solutions. There are prescriptive solutions and descriptive solutions to problems. When we talk about like the traveling salesman, for example, this is a great problem for prescriptive solutions, meaning I can prescribe a set of steps, an algorithm that a computer will follow to come up with a good enough answer, most of the time. Even for NP complete problems, we can come up with really, really good answers with prescriptive, problem solving steps. Certain problems like recognizing an image of a cat are really, really challenging for these approaches. If you think about it, if you think of like a JPEG image and you just had to look at the raw binary data that makes up that image, and you had to write a deterministic algorithm for a computer to go try and say this is a cat or not a cat, it'd be really challenging because a cat can be sitting in one of 50 different orientations. It can be one of a dozen different colors. A cat could have been in a car accident and lost a leg or something. There's lots of variations on what a cat looks like in an image. So these are areas where you want to apply descriptive solutions. I want to create a model that has seen many, many, many descriptions or training data points of what a cat looks like, so that then I can learn to recognize what a cat looks like by similarity. And I kind of embed this similarity metric into like a deep neural network or convolutional neural network, which is pretty common for vision detection problems. So ultimately, when you look at these two different types of problems, like prescriptive solutions, we need a right answer, or we need a good enough right answer. Descriptive solutions, if I mislabel an image of a dog as a cat, it's probably not the end of the world, because whatever I'm using this cat dog recognizer in, as I hope, not like a serious piece of software like the autopilot that's on my plane that flies me into the airport, or the software that controls and regulates the temperature of fuel rods in a nuclear power plant. Very obviously, we want prescriptive solutions for those kinds of problems. So when you look at security problems, and part of the reason why, or some of the early research was so bad, it was because the security engineers, they looked at ways to apply AI/ML, and they applied them to problems that weren't descriptive in nature. And vice versa, the AI/ML folks were used to using descriptive solutions for solving problems, and they couldn't identify which security problems were actually descriptive problems versus prescriptive ones. So when we did this problem breakdown for Buttercup, some of the solutions like patching, they kind of don't really fit. Like I actually need a correct answer. So a large language model is usually not the best choice here. But on the other hand, telling or writing a prescriptive algorithm that can just fix any type of vulnerability is also really challenging. So there's no good answer for either. But in this case, what we could do is we could take advantage of the fact that large language models were good at generating things, generating code. And then we added a validation step. And what that did is we kind of used this kind of hybrid approach where we're using a descriptive solution to a problem that needs a right answer, but we have a way of checking the right answer. So we can afford to generate many, many answers and use the validation to kind of enforce the constraints. So it's not always a clean delineation between this is a problem for AI/ML or this is a problem for an algorithm, but there are ways to kind of push or adjust or compensate for that if you're clever.
Yeah, no, this is great. I know we're at the end. We have covered basically all the questions that remain open. So I just wanted to thank you again for joining us today, and also give you an opportunity to share, for folks that want to get in touch with you, how they can do that.
Yeah, great. So like I said, if you want to use Buttercup, we want you to use it. It's available. It's open source. And more importantly, we have a version. I think we're one of the only people to do this, one of the only teams to do this. We have a version you can run on your laptop. You don't need DARPA's competition API. You can run it on your laptop. It's got a web interface. So please go check it out. That's at Trilobits on our GitHub organization, and the repo name is Buttercup. Please grab that. Try it out. Let us know how it works. We welcome contributions to that. If you're going to use Buttercup within your organization or really any Trilobits tools, we love to hear that. we make all of our tools to the maximum extent possible that we're allowed to by the government who's usually funding us to make them. We make them open source, so we want people to use them. We want people to contribute to them. So please don't be bashful about reaching out to us if you have questions about how to apply it within your organization. We're happy to chat with you and kind of give you some advice along the way. So you can reach me at michael.brown@trailofbits.com. You can reach us on our website. Also check out our blog. We got tons of great stories on what we did during the AI Cyber Challenge. We tried to be kind of like a wartime correspondent for that competition. So there's a lot of great information there if you want to know more. And yeah, we hope to hear from you all. Thank you so much for the time today, Dan. I really appreciate you having me today.
Yeah, thank you. Awesome conversation. Thank you, everyone. Have a good rest of your day.